3 minus 6 is 3 modes. The 3 modes are, it can be in same direction or it can be in symmetric stretching or anti-symmetric stretching. The standard enthalpy change for the formation of 1 mole of compound from its elements in their most stable states of aggregation is called enthalpy of formation. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today we are starting up session 5 from the chapter Thermodynamics. In the last class, we have discussed about relation between pressure, temperature and volume for an adiabatic process for an ideal gas, and measurement of delta U, that is internal energy, and delta H, that is enthalpy, how it will be measured by bomb calorimeter. It is also discussed in previous session. In this session, we will discuss about principle of equipartition of energy and thermochemistry. This principle of equipartition of energy, little bit additional information, but to understand about the energies you should know, and thermochemistry is a part of your syllabus. First we will understand principle of equipartition of energy. This principle is based on classical mechanics, which is state as energy is distributed or partitioned equally among the different forms of internal energy. This equipartition of energy is based on classical mechanics, and which is stated by energy among the different forms is equally distributed in internal energy. We know now what is internal energy and how it has been measured. The total energy of a molecule is divided equally among the different degrees of freedom, the amount being half kT for each mode. Here K means Boltzmann constant equal to R by N. If 1 mole of gas is considered, then the energy distributed per each mode is half RT. When a gas takes up energy, this energy distributes it equally in each of the independent ways of the molecules can absorb energy. That is into translational kinetic energy, rotational kinetic energy and vibrational kinetic plus potential energies. This is the statement of equipartition energy principle. What is that equipartition? Equipartition means equally partition or equally distribution should be there of energy. What does it mean? In a molecule, all kinds of energy will be equally distributed with respect to internal energy. For example, what they have told, when a gas takes up energy, when gas has been received some energy, that energy will be distributed itself equally as vibrational energy, rotational energy and translational energy. Also potential and kinetic energy is also there. So equally distribution will be there. That distribution will be considered as the equipartition energy principle. According to this principle, a gas on warming should take up energy in all its degrees of freedom, that is half RT per mole for each of translational and rotational modes and RT per mole for each vibrational mode. According to this principle, a gas on warming should take up energy, half RT per mole like translational and rotational mode. RT per mole means each vibrational mode. In that monoatomic gases like helium, neon, argon, sodium vapor, mercury vapor, like that, these have only 3 translational degrees of freedom. In monoatomic gases, you have to remember these points. 3 translational degrees of freedom are there. In other words, for monoatomic gases, the translational kinetic energy gives the total energy of the molecule. Total energy of the molecule 3 into half RT, so 3 by 2 RT. This is how they have been calculated. In diatomic gases like HCl, HBr, etc., in addition to 3 translational degrees of freedom, there exist 2 rotational and 1 vibrational degrees of freedom. Monoatomic means 3 translational. According to diatomic gases, after 3 translational degrees of freedom, extra 2 rotational and 1 vibrational degrees will be present. Total energy per mole, translational energy plus rotational energy plus vibrational energy. Total modes, 3 modes in translational, rotational in 2 modes, vibrationally 1 mode. Total energy per mole 3 into half RT plus 2 into half RT plus half RT plus half RT. This is kinetic and potential equal to 3 by 2 RT plus RT equal to 7 by 2. This 3, 4, 5. Okay. Overall 7 by 2 it will happen. Next, different contributions for specific heat for different gases are summarized in the following table. Specific heats of different types of molecules according to principle of equipartition of energy. See here, type of molecule monatomic, example helium or neon or etc. Translational degree 3, rotational degree 0, vibrational degree 0, CV at lab temperature 3 by 2 RT, CV at very high temperature 3 by 2 R, diatomic like H2 or HCl, translational 3, rotational 2, vibrational 1, CV at lab temperature 5 by 2, CV at very high temperature 7 by 2. Triatomic linear like CO2, HCN etc. For all translation is 3, rotational is 2, vibrational 4, 5 by 2 R and 13 by 2 R. And triatomic non-linear, this is linear, this is non-linear, H2O and SO2, translational 3, rotational 3 and vibrational is also 3, 3R and this is 6R. Usually for your next classes, triatomic, linear and non-linear is very much important. Vibrational degrees of freedom of linear triatomic molecule taking CO2 as an example. How that CO2 will be exhibited? CO2 is a linear triatomic molecule. We know that by VSEPR theory. The number of vibrational degrees of freedom 3n minus 5 equal to 4 modes. The 4 vibrational modes are sketched below. See here, CO2, this is stretching symmetrically, one side here, this side here. Bending in plane, all are asymmetric in nature. Stretching asymmetrically, one side is showing the opposite side, here it is showing in the same direction, it is in opposite direction. Bending asymmetrically, see bending all takes in asymmetric nature. So this is how the 4 vibrational modes have been shown. Vibrational mode for H2O is a non-linear polyatomic molecule. So 3n minus 6, that is the formula. 3 into 3 minus 6 is 3 modes. The 3 modes are, it can be in same direction or it can be in symmetric stretching or anti-symmetric stretching. So 3 modes. Next is thermochemistry. All forms of energy can be quantitatively converted to heat. All forms of energy can be converted into heat. Virtually every chemical reaction is accompanied by absorption or evolution of heat. Thermochemistry deals with heat changes accompanying a reaction. Carbon burns in air with evolution of heat. Carbon, it's allotrope. If we take graphite, if it burns in air in presence of oxygen, it gives carbon dioxide at the enthalpy minus 393.5 kilojoule per mole at 298 Kelvin. Ammonium chloride dissolves in water with absorption of heat. This is evolution of heat. This is absorption of heat. This is ammonium chloride. In the aqueous solution, ammonium chloride will form with absorption of heat at 15 kilojoule per mole. Here exothermic reaction also you can observe and endothermic reaction also you can observe. Balanced equations representing the chemical reactions in which the enthalpy change and the physical states of reactant and product also given are called thermochemical equations. What they are telling? In the balanced equations, chemical equations, in which enthalpy change and at what physical states of reactant or and also product has been shown. This is the states of matter and this is the enthalpy changes going to observe by seeing the reaction only. That equation or reaction will be called it as thermochemical equations. Next important features of thermochemical equations are the physical states of products and reactants are indicated. Physical states like solid or liquid in aqueous or gases, whatever the physical state of product and reactants has been present or has been shown by the reaction, that will be shown in equation also. The allotropic forms of the reactants and products are mentioned. See, in the previous reaction, carbon in the allotropic form of graphite, that also you have to mention. The enthalpy change accompanying the reaction is provided as delta H. What all the reactions with respect to enthalpy or entropy, it will show in the reaction. Temperature is indicated. In the reaction, if temperature has been projected, that will be also shown. By seeing the thermochemical equation, you will understand the physical states of reactant and product. Also, if any allotropic forms has been used, what kind of allotropic forms has been used, that also you will understand. And the enthalpy changes will be mentioned with specific rate, and temperature is also indicated. In the first example cited, delta H is negative. The reaction proceeds with evolution of heat. Such reactions are called exothermic reaction. In the before carbon reaction, there the exothermic reaction means from the reaction heat has been evolved. So that kind of reaction we'll call it as exothermic. Their enthalpy will be negative. This reaction itself. For an exothermic reaction, if less than 0, as the heat content of the products will be lower than that of reactants. The excess of energy of the reactants over that of the products is given out of heat. All combustion reactions are exothermic in nature. The excess of energy given to the environment. Reactions which proceed with absorption of heat are called endothermic reactions. Dissolution of ammonium chloride absorbs heat from the system. Absorption of heat means endothermic. Giving out of heat from the system is exothermic. For an endothermic reaction, delta H is greater than 0. The heat content of the products will be greater than that of reactant. Next, enthalpy of reaction. Heat change or enthalpy change accompanying a chemical reaction at a given pressure and a given temperature is called heat of a reaction. Whatever the heat changes or enthalpy changes will be seen or will be observed in a chemical reaction at a given pressure or a given temperature is called heat of a reaction. It is represented by delta RH. It is convenient to report the values of heat change in terms of standard states as the value of delta H varies with pressure and temperature. See here, delta H reaction equal to sum of delta H products minus sum of delta H reactants. That will be expressed in joules per mole. Standard state of a substance is taken as the most stable form of the substance at 1 atmospheric pressure, and 298 Kelvin. This is the standard STP. Graphite is considered to be more stable form of carbon than diamond. The heat of reaction at 1 atm is called, atmospheric pressure is called standard heat of a reaction. It is represented by delta H naught. Enthalpy changes during phase transformations. Phase transformations also involve energy changes. For example, ice requires heat for melting. Normally, this melting takes place at constant pressure. We know that ice needs some heat to get melt. So, there is a phase transformation. Normally, this melting takes place at constant pressure, and during phase change, temperature remains constant. H2O solid to liquid, heat of fusion will be 6 kilojoule per mole. Here, heat of fusion is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surrounding. We know water can be changed into solid like ice or can gas also. It will be reversible reaction also. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Melting of a solid is endothermic. So, all the enthalpies of fusion are positive. Here it acquires energy rather than giving off. Amount of heat required to vaporize 1 mole of liquid at constant temperature under standard pressure is called standard enthalpy of vaporization or molar enthalpy of vaporization. From liquid water, it will get vaporized. So, that is, it needs some energy, right? That energy will be called it as standard enthalpy of vaporization. See here, water into gaseous state. So, vaporization positive at 40.79 kilojoule per mole. It is the standard enthalpy of vaporization. Standard enthalpy of sublimation means is a change in enthalpy when 1 mole of solid sublimes at constant temperature under standard pressure, means direct from solid to vapor. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 Kelvin with heat of sublimation is 25.2 kilojoule per mole. For example, naphthalene sublimes slowly and for this 73.0 kilojoule per mole. Vaporization means the liquid gets vaporized as gas. So, it needs some energy or heat, that will be called it as enthalpy of vaporization. Sublimation means from solid to direct vapor, like camphor or naphthalene directly converts without melting. It is also needs some enthalpy. So it is called enthalpy of sublimation. Next, Kirchhoff equation. For enthalpy of reaction at two different temperature T1 and T2, we have delta H2 minus delta H1 equal to Cp into T2 minus T1, or delta Cp equal to delta H2 minus H1 divided by T2 minus T1, where delta Cp is difference in molar heat capacities of product and reactants. That is delta Cp equal to sum of NCP of products, sum of NCP of reactants. Delta H2 is heat of reaction at temperature T2. Delta H1 is heat of reaction at temperature T1. For heat absorbed at constant volume, delta U2, that is internal energy, has been implemented here, minus delta U1 equal to delta U into T2 minus T1. So delta CV equal to U2 minus U1 by T2 by T1. By taking equation 2 and 3 are called Kirchhoff equation. This is the very important equation. Next, enthalpies for different types of reactions. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of compound from its elements in their most stable states of aggregation is called enthalpy of formation. From the elements, it's going to form a compound formation. So it needs a stable state. After that, it form product or compound. That enthalpy is called enthalpy of formation. This is delta F H minus, where the subscript F indicates the 1 mole of the compound in question has been formed in its standard state from its elements in their most stable states of aggregation. Example, H2 plus half O2 gives H2O liquid. Here formation minus 285.8 kilojoule per mole. See here carbon at allotropic form graphite plus 2H2, it gives methane. Here all the formation is going to happen. Here also see C2H5OH, that is methanol. Next, standard enthalpy of combustion. Combustion reactions are usually exothermic in nature. These are important in industry like rocketry, other walks of life. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion and all the reactants products being in their standard states at the specified temperature. Cooking gas in cylinders contains mostly butane. During complete combustion, 1 mole of butane will be 2658 kilojoule of heat is released. We can write the thermochemical reactions of this. This is butane plus oxygen is required, means 13 by 2 O2, that is carbon dioxide will be liberated with water. Enthalpy of atomization, see here hydrogen giving out 2 molecule of hydrogen, means element is going to form as a atom. You can see that H atoms are formed by breaking of H and H bonds in dihydrogen. This is dihydrogen going to form for atoms. That is called enthalpy of atomization, and it is the enthalpy change on breaking of 1 mole of bonds completely to obtain atoms in a gas phase. From element or from any compound, it is going to form atom by breaking its bonds. Enthalpy of a reaction and bond energy. Heat of a reaction can also be calculated using bond energies of the reactants and products. Bond energy released when a bond is formed between two free atoms in a gaseous state to form a gaseous molecule. It is formed between two free atoms. Bond energy is numerically equal to bond dissociation energy for diatomic molecules. Bond energy is defined as the energy necessary to break 1 mole of bonds in a gaseous covalent substance to form products in the gaseous state of at constant temperature and pressure. Usually bond energy where it will refers to break 1 mole of a substance. Greater the bond energy, more stable the bond is, the harder is to break. Thus bond energy is measured in the bond strength. Whenever bond strength is more, you cannot break it easily, then it requires more bond energy also. But in polyatomic molecules where more than one bond of same type is present, we take the average value of bond energy. Average bond energy, total bond dissociation energy by number of bonds. Average bond energy OH in H2O is 110.57 kilocalories per mole. In H2OH plus OH, see here 119.95 kilojoule. OH in H and O 101.19 kilojoule. Total bond dissociation energy 221.14 kilocalories. Average bond energy like 221.14 by 2. Total bonds 110.57 kilocalories per mole. Heat of a reaction can be calculated by delta H naught reaction equal to sum of bond energies of reactants, sum of bond energies of product. This is about the thermochemistry. Next, what is lattice energy, Born-Haber cycle and enthalpy of solution will be seen in next session. I hope you have understood the equipartition of energy and also some of the concepts and some of the enthalpies of the thermochemistry concept. We'll meet in the next session. Thank you.